Welcome to MEI Modelling with Algorithms. We're on the topic Linear Programming 3, Application to Network Problems, and this is video 3.3, Network Flow Problems. So we're going to look at a very simple problem. We're going to think about network flow in this network here, where we have a source S and a sink T, and these numbers represent the maximum capacities of the different arcs. Now, there's no directions indicated on these, but hopefully it's obvious that SB and SC must be directed in those directions, and likewise BT and CT must be. BC, well, we could say that can go in either direction, so a maximum capacity of 1 in either direction. So just like with previous problems that we've seen based on this simple network, we've got 6 variables, but what these variables represent is going to be slightly different, because previously they were just either 0 or 1 depending on whether the arc was going to be included. Now what they are going to represent is the amount of flow travelling through the arc that they correspond to. So what that means is that the values can be non-integer, assuming we're talking about liquid or something flowing through the network. So we don't need to restrict them to integers if that's how we're modelling, if that's the sort of situation we're modelling. But what they will have is a maximum value, and that maximum value, of course, will be the capacity of the arc that's involved. So this is going to be a maximization problem because we're trying to find the maximum flow. And so we're going to need an objective function. Now this is going to be a little bit different from the previous two problems. Remember that what we've already said about network flow, everything leaves from the source and ends up at the sink, and we're not allowed to have build-up anywhere else. So all I really need to look at in terms of what the total flow is across the network is what's leaving S. So if I do SB plus SC, that's actually all I need to write. That's perfectly adequate as my objective function. I could, of course, have done BT plus CT. That would work equally well, but I'm going to choose SB plus SC. And what we need to look at as well are the constraints which are going to be involved, and these will come down to the idea that there can't be any build-up at the nodes. So for any node on this network, apart from the source and the sink, the total flow in must equal the total flow out. So if we look at node B, the total flow into that node, which is SB plus CB, that must equal the total flow out. So if I subtract the total flow out, which is BC and BT, that must equal 0. And then similarly for node C, if we look at the flow into node C, so that's SC plus BC, and then I subtract the flow out of node C, which is CB and CT, that must also equal 0. And then the really important thing, which again characterizes in a sense the network flow problem, is that each arc has got a maximum capacity. So each arc gives us a constraint. So for example, this arc here, SB, the variable associated with that, so the actual flow through that arc, must be less than or equal to the capacity of that arc, which in that case is 2. Okay, so there'd be a similar constraint for each of the 6 arcs, including the 2 either way for BC. So here's a summary of the formulation then of the network flow problem. So now we can hand it over to one of our linear programming solvers. We'll use the Excel spreadsheet one for that. This row here might look a bit strange because you might be expecting some numbers underneath to represent the objective function, which we could do, but because the objective function is so simple, it is literally just SB plus SC. We can literally just put the formula 8 that goes in here as those two cells added together. Alright, so again, if you've had enough experience using this add-in, you should be able to see why what's in here corresponds to the linear programming problem that we've set up. And once we've pressed solve and run this, we get the following results. So it's giving us a final value of 5, so that's telling us that the maximum flow through that network is 5, and then it will individually tell us the flow in each of the arcs. And interestingly enough, in this case, it's turned out that these things are all integers, but that wasn't a requirement. It just happens in this case that that's what's happened. So that concludes video 3.3, network flow problems, and concludes the topic linear programming 3, application to network problems.